So we already know that the spring force is the negative derivative of potential energy to displacement, negative du dx, which is equal to negative kx, k delta x to be exact, but you get the point there. And when we look at, say, an energy diagram of u versus x, because this is just a u versus x graph that we're going to be taking the slope of to get the force, right? The minus sign is already out there, so if the slope is negative, this whole thing becomes positive. And we'll look at it even from a simpler point of view. All right, I thought that was right. It's all basic stuff. We know that if we look at a u versus x graph and it's a cosine type graph or cosine like, if you will, then the slope of that will all be sine functions, because the derivative of a cosine function is a sine function. So as the cosine does this thing, the sine does the opposite thing, or out of phase by pi over 2. It's just the opposite direction. So this slope becomes negative. This whole function here, this whole derivative will be positive, negative, negative. We'll see examples of that working. So we look at an energy diagram of u versus x. Just like we had x versus t way back in chapter 2. Take the slope of that, get your velocity. We can determine points of stable, unstable, and neutral equilibrium. Section 7.9. So for example, if we have a graph of u versus x, looks something like this, we can say that the points of stable equilibrium first are points where there's a local minimum or the slope is equal to 0. But there's a turning point because remember, there's a spring force going back and forth. That's why this thing turns. So stable equilibrium, right, at all local minima. And we know the only one local minima here, the slope is 0. So the force temporarily is turning. That's a turning point. It's maximum kinetic energy at that location. So stable equilibrium at local minima, or when the spring force negative du dx equals 0. And classical case of stable equilibrium is when the ball hits the ground. You drop a ball, boom, and it stays on the ground. It's stable. It's not gonna, no other outside force moving it. It's gonna stay there, stable equilibrium, balance. For a case of unstable equilibrium at places of local maxima, every local maximum is a point of unstable equilibrium. And that's like when you throw a ball up in the air, its instantaneous velocity is 0, and then it turns. You know, it's actually serving as a turning point because the force due to gravity is still acting on it. But for a moment in time, the velocity is 0, and we say that it's only in equilibrium, temporarily, or it's unstable because it's going to be knocked out of balance instantly. So we have a case of U versus X that looks like it's like this. It's a turning point, but that's a local maximum. Those in calculus know all about this. So unstable. At local maxima. So car goes up a hill and then it just goes the other way. It's only equilibrium very temporarily. It's not going to stay. It's unstable. Or also when fx equals to negative du dx equals 0. Again, I'm going to spare you the mathiness of all of that, minima, maxima, because it's not important for our context. We want to get right to the point for those of us who are not in calculus, so they have just a basic conceptual understanding of when there's stable and unstable equilibrium. That's the point here. So again, let me get the example. It's like when ball hits ground, or that's classical case of stable equilibrium. Unstable is when the let's say ball is at the apex of a flight, but about to fall down. Equilibrium instantly, but it's not stable. It's unstable at that highest point. And neutral equilibrium is when the potential energy function is a constant. Still, when there's no local minima or maxima, potential energy functions are constant. The derivative is still 0. So we're just going to we're looking at the graph in 3 different ways to determine where the stable, unstable, or neutral equilibrium exists. So for example, if we have a graph like this, these are points of neutral equilibrium when the potential energy is a constant for all x, whatever that domain is, or that interval, right? Questions on that? When the potential energy is constant, slope is still 0. Three different perspectives, 3 different points of view, maybe on the same graph. Fs du dx. And it could be du dr for all spatial coordinates x, y, z, where r is the linear combination of x, y, and z. You can find the magnitude of it by taking the square root of x squared, y squared, z squared, all that 3D coordinate system. So 3 different cases. No turning points at u being constant. So let's go to a sample question. chapter 7, number 47. Page 192. And so we're going to dissect where the equilibrium is stable, unstable, or constant, or neutral. So I wanted to just cut out all the jargon. When X is greater than 0, we got to force this. I mean, we can dissect it. I mean, hopefully that's simpler. Try to speak on it as directly as possible, you know. There you go. So one point of thing before we get to that problem is like when we have a position function, it's a cosine omega t, then it's negative omega a sine omega t, then it's going to be cosine. Again, the derivative of that for the acceleration. And we know that force depends on the acceleration, which is a cosine function. So we can kind of look at the position and the force in those same terms. So like in number 47, we have what looks to be a cosine or cosine-like function. And so the derivative of that would be a sine function. Everywhere where the cosine is 0, the sine will be a maximum, and so forth. And that's exactly what's going to happen in number 47. So it's just a marriage between those two sinusoidal functions that are out of phase by pi over 2. One's positive, one's positive, the other's negative. One's maximum, the other's minimum. Back and forth. Okay. For the potential energy curve shown in figure 747, determine whether the force Fx is positive, negative, or 0 at the 5 points indicated. All right, so we're looking at the force first, and we know from our definition here that we can determine what the force is going to be. What is the slope or the derivative of potential energy at A? Any takers? Anybody out there? What is the slope at A or the derivative? Same. Yes, it is 0. I mean, it may be some confusion there because it's kind of slopey, but no, it's 0. Yeah. So it's 0 at A. So the force is 0 at A because the slope of this is the force, which is kx, and there's no x. No displacement because it's the same. Therefore, it's 0. So the force at A equals 0. And we just do the same thing, following this basic concept. This is nothing but slope, guys. Those of you who haven't had calculus, slope. You want more nuance and detail on that, you can pick up the Stewart calculus book or any other calculus book and convince thyself. But that's a slope. All right, what about B? So the slope at that point is what? You gotta be careful. I'll say F. Is that a positive, negative, or 0 slope at B? Now remember, this is already negative here. The slope is negative, but the entire thing becomes positive. Yes, but yeah. So the slope is negative of the thing that we already have. So the force is positive. Yes. I want to get that middleman in there so we could all see that. Yeah. And the equilibrium is neither anything at that point, because by definition, if we will, we're defining stable and unstable at minima and maxima, and also neutral where the potential energies are constant. And we know that the derivatives of constants are nothing. That's why A is equal to 0. So yeah. Okay, then at C, what is the force going to be there? Anyone else? Lily, Joya, Christian, anybody? Okay, one for anyone else want to answer that? I know you got it. Anybody else unsure? We're looking at that graph there, and we're trying to figure out whatever the slope is. That's going to tell us, something about the force. Well, for example, at B, the slope was negative. Yes, true, fine. But this is already the definition of force is negative, so negative makes it positive. So it will also be 0, yes, because there's no slope at C. No slope, no derivative, no nothing. It is 0. So basically what's happening is in part B, for example, the force is trending, like if we have a horizontal mass spring system, the force is trending to the right. It's a positive direction, even as we are losing potential. Because if you look at the graph, it's going from 4 to 2 to 0 and so forth. So yeah, so at C it's 0, and then D, what is the force at D? So the way to dissect this, if those might be confused, is like, take a look at what the slope is at that particular point. You can assign it to the outside of this definition. This is even before you get to the nuance, if you will. It's positive. This entire function is positive. Therefore, the entire thing for force is negative, because negative times positive. And that's basically what we did here in part B. The slope is negative. Well, the slope of the entire function is negative. Well, it's negative, positive. And then for part E, that's also 0 as well, like A. They seem a little off there, but so that is your stuff. And if the force is 0, there's no displacement. So that's when that potential energy is a turning point. So the force is going through equilibrium, and then it's going to start increasing. So going to the left, restoring force right, 0. Restoring force left, negative, 0, positive, 0, negative, 0, back, forth. If you look at it from a mass horizontal spring, mass spring system, horizontal mass spring system. Yeah. Any questions there? It's all part A through E. Okay, so why don't you now do parts B and C, and we'll come back in 5 minutes and talk about that. Indicate points of stable, unstable, and neutral equilibrium. Sketch the curve for f of x versus x from x equals 0 to x equals 9.5 meters. Yeah. All right.